Okay, so next we're going to look at an example for the Frobenius method. So these will be different examples, and the different examples basically will be different Bessel equation. First would be of order 0, then we do the one of general order, which would be mu. Okay, but let's start by the simplest case. So in this case we have given Bessel equation will be sec x squared second derivative of y dx squared plus x dy dx plus x squared of y to be equal to 0. Okay, so we can rewrite this equation as the general form of an ODE that would be d squared y dx squared plus this will become 1 over x dy dx. Basically I'm just dividing by x squared plus y equal to 0. So in that case, note that px will be equal to 1 over x, and q of x, which will come over here, is equal to 0. Okay, so by looking at the ODE, you can see that this equation should be singular at 0. Okay, so the ODE is singular at 0. So basically that means that x sub naught will be equal to 0 on the when we do the Bessel, the Frobenius approximation. Okay, so in order to know if we can apply the Frobenius approximation, we first need to do a check. Okay, so a test to know if we can apply the Frobenius approximation. Okay, as we know before, we need to check that the limit of, okay, let me just write it here, x minus x sum naught be x, as x go to x naught, in this case is 0, and the limit of x minus x sum naught square qx are finite. Okay, so this will mean that here this is equal to the limit as x equal to 0 to what? X, and px is 1 over x, so the limit will be what? 1. And here the limit as x goes to 0 would be x squared times qx would be 1, so this will give you a limit of 0. Okay, alright, so those two are finite limits, so that means that we can use the Frobenius approximation. Okay, so assuming Frobenius approximation, which would be what? Which is the y of x is equal to the summation of n equal to 0 to infinity of a sub n x of n plus k. Okay, and as previously, we need to take the first derivative. Hopefully I'll be able to fit everything in here, so this will be summation to n to 0 infinity a sub n, n plus k, x of n plus k minus 1. And the second derivative would be summation n to 0 to infinity coefficient a sub n plus k times n plus k minus 1 x of n plus k minus 2. Okay, and now we're going to substitute this into this equation over here. All right. So that should be page 187. Substituting into ODE. Okay, again the ODE is this equation over here. Okay, so what do we have? We're gonna have x squared times the second term, so summation n equal to 0 to infinity a sub n plus k n plus k minus 1 x of n plus k minus 2 plus x n equal to 0 to infinity dy dt, which is a sub n plus k x of n plus k minus 1 plus the last term that I might be able to fit over here, plus x squared of the summation n equal to 0 to infinity a sub n x sub n plus k. Okay, and all this is equal to 0. Okay, so let's just develop this x squared here, this x and the x squared, and see what happens. So that means here we're gonna have summation n equal to 0 to infinity of a sub n plus k n plus k minus 1 times x. So you see this one will cancel. Oops, sorry for that. You cannot see this x squared will cancel this x minus 2 over here. So we end up with n plus k. Now for the second term, we're gonna have plus, so this x will cancel this minus 1, so plus summation of n equal to 0 to infinity of a sub n plus k x to n plus k. Alright, so far that's everything convenient because we have both of them with the same x to the same power. So, and the last term over here would be plus summation n equal to 0 to infinity a sub n x of n plus k, but this is the one which is gonna gives here a problem. This is n plus k plus 2, and this should be equal to 0. Okay, or we can just rewrite this as, let's collect terms, so this will be summation n equal to 0 to infinity. So let's do here a sub n factored by a sub n of n plus k n plus k minus 1 plus n plus k of this term over here. Alright, and this would be x to the n plus k plus the last term over here plus the summation n equal to 0 to infinity a sub n x of n plus k plus 2. Okay, so what do we know about this equation? In order for this equation to be satisfied, okay, let's say when this an is different than 0, can only be satisfied because this is always equal to 1, okay? Never equal to 0, x to the power. So these two terms, either this one or this one, must be equal to 0, okay? So here, let's see what happened. For this to be equal to 0, let's see what happens. So for the above equation to be satisfied when a sub n is different than 0. So basically this is the trivial solution. Each term must be 0. Okay, so let's see what happened for the first term over here. So alright, so then we're gonna have that n plus k minus 1 plus n plus k here needs to be equal to 0. And you know, initially on the Frobenius method, we first try to solve for k. So in that case, you say set n equal to 0, and this will give you what? This will give you k factor of k minus 1 plus k equal to 0. So if we develop that equation, you can see this will be equal to k squared minus k plus k equal to 0, which in this case means that k squared is equal to 0, okay? Which will mean that the two roots will be k will be equal to plus minus 0. Okay, really this means that k1 equal k2 equal to 0. Okay, so basically we are on the case of repeated roots. And in that case, if you go to the previous notes, you know that the general solution will be of the form y of x equal c1 y1 of x plus c2 y2 of x, where you will have that y1 of x will be the summation from n equal to 0 to infinity. So this is the traditional one, x of n plus k. In this case, k is 0. But now the difference will be y2 of x, since it's repeated, will be equal to the same one over here, but it needs to be with different coefficients. So let's say we call them b sub n, x of n plus k. This would be k1, this would be k2, but they're both 0. And now you cannot add the same solution, so it would be plus y1 of x log of x. Alright? So now that's when everything becomes a lot more work. So now we assume this solution, now that we solve for k, we need to repeat the whole process, but this time for this solution and then for this one. Okay? In order to solve for a sub n. We solve for k, now we need to solve for the a sub n by substituting the y sub 1 equation back into the initial ODE. Okay, so let us first find y sub 1 of x. So we know that y of 1 of x is what? Summation n equal to 0 to infinity a sub n x of n plus k. So this is going to be pretty repetitive, so this will be dy1 dx equal to the summation to n equal to 0 to infinity a sub n plus k x of n plus k minus 1, and the second derivative will be equal to n equal to 0 to infinity a sub n plus k minus 1 x of n plus k minus 2. Okay? Alright, so now we substitute into ODE, and what do we have? Basically it's the same as before. Okay, so I'm going to start going a bit faster. Would be x squared. But now, okay, maybe here I went too fast because this is 0, so we can do simplification, and this one is 0. So this will mean that, let's see if I have space, this one would just be summation n equal to 0 to infinity of a sub n x sub n. This would just be summation to n equal to 1 to infinity, because now it's just like the legender, we don't have this k that can be a real number. So this will always be a natural number. So this is 1 over here, and then we'll have a sub n times n of x of n minus 1. Okay, because k is 0. And for the last one here, we'll have summation from n equal to, for the same reason, to infinity to a sub n times n minus 1 x to the n minus 2. So this will simplify everything when we go and substitute. It will be a little bit faster. Okay, so basically this will be what? Summation x squared n equal to infinity a sub n times n minus 1 x to n minus 2 plus x of summation of n equal to 0 to infinity a sub n times n of x to n minus 1 plus x squared of n equal to 0 to infinity a sub n x sub n. So basically you see that now this becomes just like the Legendre method, okay, once you go to the second step. Alright, so let's just see what happens when we develop these polynomials here. The x squared, this will give a summation from n equal to 2 to infinity a sub n minus 1 x to the n. Oh, this is 1 over here, sorry for that again. Alright, plus here the summation n equal to 1 to infinity of a sub n times n x to the n plus summation from n equal to 0 to infinity to a sub n x to the n plus 2. and this will be equal to 0. Okay. All right, so now let's go one term at a time if you want. Let's see this one. Let's move it on the same index. Okay, this is my 2, and here this is 1. So let's move this one to 2. So this will be equal to what? This will give us summation from n to 2 to infinity. So we leave that one unchanged. A sub n times n minus 1 x of n. Plus, now what happens is that we want to start this one at 2. So that means, what do we need to do first? We need to put outside the first term. So it will be n equal to 1 will be what? a1x times 1 times x to the 1. Okay, so it will just be a1x. And now we put here plus, this will be the same thing here, summation from n equal, but now it's 2 to infinity, a of n times n x to the n. So basically, this is this term over here. Alright, so these two terms over here correspond to this one. And now this one, they have the same, so we have, you see they have the same power n. This one we can leave it unchanged. A sub n x to the n plus 2 is equal to 0. Alright, so we can combine over here these two terms. So this will give us what? Summation n equal to 2 to infinity factored by a sub n, and we're going to have n times n minus 1 plus n for this term. This will be x to the n plus a1x plus the summation of n equal to 0 to infinity to a n x n plus 2 equal to 0. Okay, so you can probably see that this term over here will just be equal to what? N squared minus n plus n. So that these two terms will cancel out. And then we have again the problem that we don't start the summation from the same point. Okay, but let's not do too much in one step. So let's first say this will be equal to summation from n equal to 2 to infinity a sub n times n squared x to the n, okay, plus a1x plus summation from n equal to 0 to infinity a sub n x of n plus 2 equal to 0. Okay, so let's say we want to transform this one to n equal to 0. Think about this about polynomials. Okay, if you start at 2, what do you need to do with this one so that at step 2 you end up with x to the n again? You need to do here an n plus 2. Okay, people like to do it this way, but basically that means you need to set m equal to n minus 2. I don't like to do it that way, so that n equal n plus 2, whatever is easier for you. I like to do it in one step, okay? But if we do it that way, what will you have? You will have that this term over here becomes what? Will become summation from m equal to 0, and then we have to switch the index again of a. So this is n will be a of m plus 2, okay? then this term over here will become what? n plus 2 square x of n plus 2. So all this will be this term over here. All this term plus a1x plus summation of n equal to 0 to infinity a sub n x of n plus 2 equal to 0. Okay, personally I like to do this step directly here to here, but then now in this step generally you say m equal n. But if you do it directly, basically what do you see is what is that after the second derivative you need to have n plus 2. So this will be all n plus 2. So basically you have the same thing, n equal to 0 to infinity. You see you end up with the same thing. You need to put a plus 2 over here, so that means this becomes a n plus 2 times n plus 2 square x of n plus 2 plus a1x plus summation n equal to 0 to infinity a sub n of x n plus 2. So now that we have everything from the same summation sign, and here we're lucky to have the same exponential as well, we can collect the terms, and we're going to have what? a1x plus summation n equal to 0 to infinity of what? a n plus 2 times n plus 2 square plus a n. This will be to the x n plus 2 equal to 0. And now you see that you can see some type of recurrence expression. Alright, so in this case, what do we know again? Each of these terms needs to be equal to 0 in order for to be satisfied. So let me go to the next page. So 189. Okay, so let's see. Here we know that each term on left hand side must be 0. Okay, so in this case we can have x equal to 0, but that's not the solution we are looking for. So a1 needs to be equal to 0, so we can find the recurrence relation. So each term on left hand side must be 0. So that will mean what? a1 will be equal to 0, and then this term into brackets will also need to be equal to 0. So that can only happen if a1 equals 0 and the term in bracket and an plus 2 times n plus 2 square plus a sub n equal to 0. Okay, so from the second relation here we find that a of n plus 2 divided by a sub n will be equal to what? Let's see, would be equal, so this will move to the other side, would be minus 1 divided by n plus 2 square. Okay, so here we have our recurrence relation. Okay, in addition, you remember we need one for the even, one for the odd. So since a1 equals 0, right, that means that a 3 equal a5 equal a7 equal a of 2n plus 1. This is all there. So it will be, let's see, this will be the 6, 5, yes, it will be so 1. This will be all the odd. All this needs to be equal to 0. Okay, so odd and for the even we use the relation order. So for even coefficients, let's say if n equals 0, what do we have? A of 2 over a0 will be equal to minus 1 over 2 squared. If n equal 2, we'll have a4 over a2 will be equal to minus 1 over 2 plus 2 square. Okay, and now we can say that as before, a4 over a0, using the fact that a2 will be equal to minus 1 over 2 square a0 would give us what? So it will be 1 over 2 plus 2 squared, 2 to the 2, okay? Which in this case, this is equal to 1 over, we can do this one to be equal to 2 times 2 square times 2 square over here. Alright, and one more example for n equal 4. That means we'll have a6 over a4, which will be equal to minus 1 over 4 plus 2 square, which will be equal, so let me equal to minus 1 of 3 times 2 square, and now that means that a6 over a0, this time we'll be using what? The fact that a4 is equal to this relation here, 1 over 2 times 2 square, 2 square. Let me go to the line here. So this will mean that a6 over a0 will be equal now to minus 1, 3.2 squared times 2.2 square times 2 to the square. Okay. Alright, so you found the coefficients. So we can say now the solution y1 of x is what? So remember, we had y1 of x. We wanted this to be equal to the summation n equal to 0 to infinity a sub n to x of n plus k. But again, k was equal to 0, so we had this to be equal to summation of a sub n x sub n. Alright, and from here on top, we know that we only take the even cases because all the odd coefficients will be equal to 0. So that means that this will be equal to a sub naught plus a2x squared plus a4x to the fourth plus so on, so on, so on. Alright? So again, here you factor out by a sub naught, you end up with 1 plus a2 over a0 x squared plus a4 over a0 x squared plus so on, so on. So we calculated those coefficients over here. Okay, so we could go and substitute. So this would mean that y1 of x is basically more or less equal to a sub naught factor of 1 minus x squared over 2 squared. That was the first term that we had over here, a2 over a naught. The next one is a4 over a naught, which is over here, all right? So this will be equal plus, and we switch signs. This one was positive of 2 squared times 2 squared, and this is now times x to the fourth plus so on, so on. So all the above can just be rewritten as y1 of x equal to a sub naught summation from n equal to 0 to infinity, but just taking the even ones, of minus 1 n factorial square. So this is this term over here times x divided by 2, which would be this term over here to the 2n. Okay, so basically this will be the solution, will be the coefficient. This is the coefficient a sub naught, and this one. Okay, so next, the only thing I'm going to do is say the expression for y1 of x is generally known as the first as the Bessel function of the first kind of order 0. Okay, so basically you have j naught of x will be equal to summation of n equal to 0 to infinity to minus 1 over n factorial square of x over 2 to the 2n. This is what is known as the Bessel function of the first kind of order 0. So j is for the first kind, and the order generally would come here. You will see these different functions that are j to the mu. This is the order of the Bessel function. Okay, so in this case it's order 0. And it's not really y sub 1, is, let's say, y sub 1 divided by, so to be accurate, divided by a naught is generally known as the first Bessel function of the first kind of order 0. All right. So I'm going to do a quick plot just for that one here, and then I'll show you more of these Bessel functions. So it'll be y. This will be x over here. And basically this function will start at 1. And then basically it starts like a damper. Start this, and then we start going smaller and smaller, okay? So here will be the roots, mu1, mu02, mu03, mu04, okay? Every one, this is an intersection. So here, 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 oops, and okay, this is also 1. Okay. All right, so these are the roots of the polynomial. You want me to show you more of these polynomials? Let me close all this stuff first. We can come here. I think that's the code. Let me run it very quick. Okay. Oops, that's not what I wanted to do. Sorry for that. That's not the one I was looking for. That's the one. So why can I not run it over here? Okay, I guess it's still running the other one. Or let me cancel this one here. Let me go back here and run this one. This one should be very quick. So this one, we'll see this one later, but right now you see the j of the first order. This is the one in blue, and you have then of the different kinds using the same equation 1, 2, 3, 4. Okay, basically you see the different colors, but they all kind of behave the same way, and they all kind of go to 0. If you think about it, it's like every time you assume the solutions, generally you will assume solutions like you can, if you use the Fourier expansion, you can approximate everything in function of cosine and sines. If you look at this, this is kind of similar, but it gives you the possibility to have larger values at point of singularities. You see, so it's like having a sine function or a cosine function in this case, where the amplitude is not constant throughout the 360 degrees, but varies. Okay, this is a different way to approximate a equation. All right, so let's go back over here. All right, so let me see what's going on. We don't want to pause anything. All right, so let's keep going. So next, now we need to find the second solution. So the second solution, y2 of x, must be determined. Okay, so the general form of the second solution was what? y2 of x was equal to the summation n equal to 0 to infinity b sub n x of n plus k, but k is equal to 0, plus y1 of x log of x, okay? And in this case, we know that k is equal to 0. So here, I'm not going to do it, everything, but I'm going to start it. What would be the general approach? So once again, what you will do is that you will calculate dy y2 dt, you will calculate the y2 dt, okay, which in this case, okay, so I did not write it down over here. All right, so maybe let me trash this page. Because y2 of x will become a bit complicated, will be the first term is unchanged, bn x of n plus, but now what was y1 times the summation of n equal to 0 to infinity to minus 1 over n factorial square times x over 2 to the n, and all this times log of x. Okay, so in this case it's not that complicated, but what would you do? You would take here the first derivative, that will be, for the first time, will be summation of n equal 1 to infinity b sub n times n x of n minus 1. And in this case you need to use basically the so let's say you assume this is a function u, this is a function v, and you will do plus u v prime plus u prime v, okay, or you can do reverse. All right, you can carry this, again it's long, and then you do the same thing for the second derivative of y2 over 2. So this will be equal to what? Here will be n equal 2 to infinity b sub n times n minus 1 times x of n minus 2, okay, plus over here now you need to take the derivative of these two again, doing the same thing, okay. So basically you will see it becomes long, but the good thing is that all these terms here are kind of constant, adjusting function of x. All right, so you do this, then you substitute into the ODE, which is what in our case, what is the ODE? Is again that equation here, the x squared d squared y dx squared. So you substitute into that equation, into ODE, which is x squared second derivative of y dt squared plus x dy dt plus x squared y equal to 0. Basically the same step as before. And now what you're going to have is what? After doing all this algebra here, we do all this stuff to find now what? A recurrence equation for b sub n. Okay? So after doing all that stuff, you will find a recurrence equation for the b sub n's. Once you have that, now you can find y2 of x. All right, and actually after, I'm going to say some, but it's really a lot of algebra. It is obtained that y2 of x is a little bit of an ugly expression, but it's 2 over pi log x over 2 plus gamma. Gamma is the Euler constant, of the first kind Bessel function of order 0 plus n equal to 1 to infinity 2 minus 1 n plus 1 2 to the n times x to n divided by n factorial square times 1 plus 1/2 plus 1 to the n. And let me not forget to close the bracket. Okay, so in this case, we can say that where y2 of x in this case will be called capital Y0 of x is known as the Bessel function of the second kind of order 0. Okay, and this function here is the y that I showed you before in this one over here. So you see they are singular at 0. The first one is singular at 0. It goes all the way down, but it's never going to touch it. Okay, and basically after a while it becomes almost like a sine or cosine wave. Okay, with slowly the amplitude diminishing. Okay, so we are almost there. So now we can say the final solution or the general solution. The general solution of the 0 order Bessel equation is what? Will be y of x times the constant c1 times the Bessel function of the first kind of order 0 plus c2 times the Bessel function of the second kind of order 0. Okay, and this will be the end of the derivation, even though I did not do all the details here. Okay, all those details here, really they are not that bad to do. If you do it by hand, yes, it can be pretty tedious because of this derivation, of this differentiation here. But if you use some type of a MATLAB software like MathCAD, Mathematica, I actually use Maple. It's not that tedious. Okay, if you want one of the example, I will show you one of my Maple files where I can carry all this stuff. Basically just the algebra, and then I do the manipulation of this kind here, you know, with the indexes and so on the piece of paper. Okay, so